Hello. In this video, we're going to prove the sequential criterion for the convergence of functions as x approaches c, some limiting value. Or in other words, we're going to provide a theorem with proof that gives an equivalence to the definition that we introduced in the last video lecture. Right, so we say that the limit of f equals L as x approaches to c if we satisfy this definition that we gave last lecture, which turns out to be equivalent to saying that if f is defined on domain A, then for every sequence in the domain where the terms do not equal c for any of the terms, if those sequences converge, then the limit of the function evaluated at those terms converges to L. Okay. So, and this is for every sequence in the domain that converges to C. Okay, any sequence, as long as it converges to C, we evaluate that limit, which again, this right here should be thought of as a sequence, f evaluated at xn for each natural number n, that is some sequence, that should converge to L, regardless of what the sequence looks like, as long as it converges to C, and as long as that limit does indeed exist. Okay, so let's go ahead and prove this now. We're going to first prove I implies double I, and then we're going to prove that double I implies I. Okay, so proof, and this is I implies double I. So we're going to assume that and then show that that implies the statement given in part 2. Okay, so let's say assume that the limit as x tends to c of f is equal to L. And then we're going to pick an arbitrary sequence in A that converges to C with x of n not equal to C for any of the terms. We're going to pick one of those and then show that this holds here. So assume this and assume that. And let's x of n the sequence in A with x of n not equal to c for all natural numbers n. So that the limit of x of n is equal to c. So again, I'm just making my assumptions in order to show that I implies double I. I assume that, and then I take an arbitrary sequence in A that satisfies this, and then it's up to us to show now that the limit actually equals L. Okay, so how can we do this? We're going to say maybe, well, I know we're going to need an epsilon, so we'll say let epsilon be greater than 0. Okay. So then let's go ahead and look at what this assumption here means. So let epsilon be greater than 0. Then there is some delta greater than 0. So that 0 less than x minus c less than delta implies, I'm just stating the definition, the distance from f to L at x is less than epsilon. That's just stating the definition. Now, can we use that and that together now? We need to show that that must hold. well, we have this information here, right? So then we can say, furthermore, there exists some capital, yeah, there exists some index k. Okay, I'll go ahead and say with respect to epsilon, some index, so that the distance from xn to c, because xn converges to c, is at most delta for all n greater than or equal to k, is epsilon. Okay. So, however, like if xn is minus c is less than delta, right? Then it satisfies that, which means that f of xn satisfies this. So then we can say thus, the distance from f to evaluated xn in the sequence minus L is less than epsilon for all n greater than that k. Greater than or equal to k epsilon. Oh, that's it. That's this definition. If we treat that like a sequence, for all n greater than this, arbitrarily close to L, we can say hence the limit of this sequence is equal to L. Yeah, that's it. So notice how I kind of pieced this together. I really didn't know where to go. I just made my assumption, and then I wrote down the first definition, and then I wrote down the second definition, and I just looked at them, and I was like, oh, this means that, which means that, which implies that. And that shows that this converges to the limit because epsilon's arbitrary, right? Okay, so we've proven I implies double I. Okay, so now, I don't know if I'm going to be able to fit this. Try to start here. So now we're going to do double I implies I. We want to show this implies that. Okay, now we can do a direct proof, a contradiction proof, or a contrapositive proof, right? The contrapositive proof would say that, so if this then that means if not this then not that. So if we do the contrapositive, we assume not this definition implies not this. Okay. No, is that the best way to do it? Now let me think. I think your book does contrapositive. I'm not sure if that's the best way. I try to clean up your proofs, your textbook's proofs when I can. Yeah, let's go ahead and try the contrapositive. I think that might work. So I should probably recall what this definition is, like in yellow here. So epsilon greater than 0 implies there's a delta greater than 0, so that x in the open neighborhood of C implies f of x, oh, this is delta neighborhood. implies f of x is an element of the epsilon neighborhood of L. So this means, and I should probably write the quantifiers here. This is for all that there exists that such that, right? So that's a really brief way of writing it. So for epsilon greater than 0, there exists delta greater than 0 such that this implies that, using logical quantifiers. Okay, so if we go by contraposition, so by way of contraposition, and we're trying to show I, double I implies I, we need to show that not I implies not double I. So not that means that there exists a delta. If we negate this, there exists delta, because the negation of for all is there exists. There exists epsilon, such with for every delta, because the existential becomes a universal quantifier. And then if we negate this, we get, so this is, yeah, so it's this and not that. That's the contradiction proofs. So what we're going to do is we're going to say, suppose there exists epsilon. So by way of contradiction, suppose there exists, and we'll give it a specific name because there exists, and one of them, like there could be just one. So there exists epsilon not greater than 0. So that universal becomes existential. There exists epsilon greater than 0. Okay. So then this existential becomes universal. So there exists epsilon not greater than 0. So that for every delta greater than 0, every delta greater than 0. Okay. So now we need to negate this. The negation of this is that and not that, like thinking back to contradiction. So that for every delta greater than 0, if x is in there, then x is in that neighborhood and f of x not in that neighborhood. The wording is a little weird with this, but yeah, so I'll just write it out. So that for every delta greater than 0, x is in the delta neighborhood of C, and so x is in there and f of x is not in the delta epsilon neighborhood of L. It's ugly epsilon. It's even an uglier epsilon. Yeah, you can't even see it. Epsilon. Yeah, you can see it now. Okay. So how does this help us, right? So we need to show the negation of this, right? So, or that doesn't hold, right? Okay, so then, so for every natural number n, we're going to look at a sequence. So for every n, it's a natural number, okay? There is, for any sequence that you're looking at within a delta neighborhood of C, there is xn with, oh, I should have said it's about weight with position, suppose that. Somewhere in here, I probably should have said that xn is a sequence in a set difference C. Okay, somewhere in there I should have wrote that. So then, right there. Next, let xn be a sequence in a set difference C. Then, for every n, it's a natural number, there is xn with that 0 less than xn minus c less than delta. Okay. And we can choose our delta equal to 1 over n. And you'll see why we're going to do that in a second, because we want that to converge to C. So what we want is we want xn to converge to C, but the limit to not be equal to L. So for every natural number n, there is xn with that, right? Because of that convergence, or because we want the convergence, I apologize. And we know that natural number satisfies this. So that and f of xn, since it's not in the epsilon neighborhood, minus L greater than or equal to epsilon. Okay. So, okay. Okay. Okay, so here xn converges to delta, converges to C, but f of xn does not converge to L. So and because here this is always greater than epsilon for any choice of epsilon, or for there exists a choice of epsilon, not there, so that will never be within that distance, so it doesn't converge. So we can say limit f of xn not equal to L. Because that converges to L whenever for any choice of epsilon, this choice doesn't work, so it can't converge. So that proves the contrapositive of 2 implies, or double I implies I. Okay. It's a little messy, but I hope that you're able to look at this and then fill in the details. It's an important equivalence of this definition. So this definition is the same thing as saying this, which this can be useful sometimes in establishing the convergence of a function as x tends towards some limiting value c. Okay, thank you for watching, and then we have some more theorems to prove in the following videos.